Okay, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another exciting physics lesson. Inshallah, this one will be exciting. Bidnillah. Okay, we are talking about graphical representation, which is basically a fancy word of saying we're talking about graphs. Okay, so we're talking about position time graphs, we're talking about speed and velocity graphs as well, and dot diagrams. And it's not so hard, so let's just dive right into it. Let's go. Here we go. So before we start, I want you to watch this video. It's a really useful video, and it's how does a ticket timer work. So if you actually go to to YouTube and you Google that, how does a ticket timer work, this will come up. This video will come up, and it's a very good video. It just explains it in about 2 minutes, and it's a very good video. Right, so basically, in short, a ticket timer works by having, so you have a car, or you have a toy car, or you have a marble, or whatever, and then it's attached to a wee tape. And then the tape goes through a machine, so we have a machine, and the machine puts like an ink dot on the tape. 50 times a second. 50 times a second, or 50 hertz. Now, as the car moves forward, what's going to happen to the dots? They're going to be further and further apart. Now, depending on the motion of the car, there's going to be a pattern. So the dots are either very far away from each other, or they're very close to each other, depending on what's happening with the car. So if the car's moving very fast, then obviously the gaps are very far apart, like you see in this example. But if the car is moving at constant speed but moving slowly, then the gaps are going to be way less, and so on and so forth. Okay, so let's look at some examples. So here's some examples. What's happening in the first scenario? The first scenario shows a car that's moving constantly rightward velocity. So it's moving at normal velocity or constant velocity towards the right. What's happening in the second example is you see the dots are very close together initially. Let me just change the color. Green. The dots are very close together initially, but then they are further apart. So that means the car's moving faster. It's accelerating. So that's rightward velocity and rightward acceleration. What's happening in the third one is we've got deceleration towards the right or acceleration towards the left, which is exactly the same. So it's slowing down. Rightward velocity and leftward acceleration. So leftward acceleration is the same way as saying rightward deceleration. So deceleration in the right direction is the same as acceleration in the left direction. Okay. What's happening in the fourth scenario? We've got the car moving at constant speed for a while over here, and then it starts speeding up. So rightward velocity, first slow with constant speed, and then accelerating with high speed. Yep. And then finally we've got slowing down and then speeding up again. So slowing down because the gap is getting smaller, and then speeds up again. So deceleration followed by acceleration. Okay, moving on. What is a position time graph? A position time graph is a graph that has position on the y-axis and time on the x-axis, and here are some very important points. So sometimes referred to as a distance versus time graph, sometimes referred to as a length versus time graph, or position versus time graph. They're all the same. It's all measured in meters. It's used to show the object's position at any given time. Okay, so that's what it's used for. Position is on the y-axis, so this is where position goes, and time goes on the x-axis. Gradient represents speed. So if gradient represents speeds, then obviously this is constant speed. Why? Because the gradient is not changing. The gradient over here equals the gradient over here, which means it's not changing, therefore it's constant speed. What about this example over here? Okay, I'm just going to give you another example now, and you tell me what's happening. Over here versus the one in red over here. Which one's going faster? Well, Remember, the gradient represents speed. Where does it say that? Right here. Very important point. So if gradient represents speed, which one has a steeper gradient? Well, this one here or this one here. Well, obviously it's the blue one, so that one is faster. Okay, so the blue one's traveling faster than the red one, right? And they're both constant. What does that mean, they're both constant? It means they're both not changing. If I measure the gradient for the blue line over here, and I measure over here, and I measure over here, it's always staying consistent, so therefore it's always the same. It's constant. What about the red one? Over here and over here, the gradient is the same. This is the gradient, and this is the gradient, and it's exactly the same. Therefore, we're talking about constant speed for both scenarios. How do I know it's constant speed? It's a straight line. Easy. If it's a straight line with no waves and no changing and no ups and downs and no curves, then it's constant speed. Okay, so we've got a question over here, and my face takes over all of this stuff here, but it should be okay. So that says 0 over here. What was the starting position? Well, to get to the position, we need to look at that. What I want you to do when you're watching this video is I want you to pause it. I want you to try and solve it before I solve it. Okay, remember, you learn how to swim by jumping in the water. You learn physics by actually doing it yourself. So what's happening here? What is the starting position? The starting position is 0. How do I know that? There it is. The person is running. That is the starting position. So the starting position is 0 meters. What is the final position? The final position is over here. It's 150. And what is the speed, the gradient of the runner? The speed is going to be rise over run. So it's got to be 150 divided by 30, or 5 meters per second. But guess what? You don't have to take the 150 divided by 30. Because, as I said, let's go with purple. I like purple. It's a straight line, so it's constant speed. So you can actually take this one here. Okay? So you can go 50 divided by 10, and that also gives you 5 meters per second because it's constant. What about 100 divided by 20? That also gives you 5 meters per second, and so does 150 divided by 30. So there you go, 5 meters per second. And it's positive. How do I know it's positive? Well, it's moving forward. The person's position is increasing. At 10 seconds, they're at 50. At 20 seconds, they're at 100, so they are positively increasing. Okay, here we go. Slope is the ratio of rise over run. The bigger the slope means the steeper line, which means faster speed. So we've already explained that one. Straight line also means constant speed. Here we've got a scenario of 2 cars, the blue one and the red one. And as you can see, if you can get past my face, let's see if I can move my face out of the way for a bit. Here we go. So you can see that, oh, is it still working? There we go. It goes to 120. That's okay. Right, so let's put my face back where it belongs. So what's happening here? What is it asking for? What was the starting position for the blue car? The starting position for the blue car was at 20. And as you can see from the graph here, it is at 20. So the starting position for the blue car is 20. And for the red car, it's at 0. Because remember, this is the position over here. So it's at 0. Right. Even though it came in at 4 seconds, but it still started off at 0. But if we extrapolate that, as one of my clever students said, Al-Hudayb, right? If we extrapolate that, we can see that the actual starting position is actually more like maybe minus 60. Okay? But you don't have to worry about that now. Right. So the car is going faster. Which car is going faster? The red car is going faster because it's steeper. The slope is more prominent. The gradient, the slope, the steepness, all of them mean the same thing. Is the speed constant? Yes. Why? There's no changes in the speed. The gradient here equals the gradient here. Okay? So the gradient is the same. It's a straight line. It's not a curve. It's not one of these or one of these, which we'll talk about as well. But since the gradient isn't changing, it's constant speed. Okay. The direction of the slope shows whether the object is slowing down or speeding up. Yes. Although this is not correct. It's not slowing down. It's just going in a negative direction. So that is incorrect. So this one is speeding up. This one could also be speeding up. It's just going in reverse. So it's not necessarily slowing down. It's just going in reverse. And I'll explain the difference soon when we get to it. Here we go. That's it. That's when we get to it. Right, so what is happening in each one of those scenarios? Now, they might look a bit confusing. I don't want you to be confused. I promise you, it's easy, very easy. What you need to do is very simply look at the tangent. Remember that from what? From maths. From maths. Do I have a ruler here? I don't have a ruler. It'd be cool if I did, but I don't. So let's just cover that up real quick. I want you to look at the tangent. So I'm going to draw a tangent over here, and then I'm going to draw another tangent over here. And a tangent is a line at 90 degrees to the curve. So there's one, and there's another. Once I draw the two tangents, I can see that the gradient changes. But what's happening to the gradient? The gradient is getting steeper, so that means it's speeding up. It's speeding up, and it's going in the positive direction because that's positive, and this is negative. So basically it's speeding up, which means it's accelerating in the positive direction. So that's what that means. Speeding up means accelerating in the positive direction, or positive acceleration. What's happening here? What's happening here is a different scenario. We've got, let's draw the tangent one more time, and we can see it's also speeding up. Wait a minute. This is speeding up and this is speeding up? Yes. Except this time it's speeding up in the negative direction. It's like a car speeding up in reverse. So the car is still speeding up, but it's going backwards. So it is speeding up, but in the negative direction. So what do we call that? We call that negative acceleration, not deceleration. Deceleration is slowing down. So this is negative acceleration. It just means the car's in reverse. What's happening over here? Well, again, let's draw the tangents and find out what's happening. This time it's slowing down. It's clearly slowing down because the gradient is less. Over here, it's less than over here. So the gradient is getting smaller, therefore it's slowing down. It is decelerating, but it's still positive deceleration. How come it's positive deceleration? Well, because it is slowing down. Deceleration. Makes me think about celery sticks. Deceleration. Because we're still going towards the positive. What about this guy over here? Now let's have a look. And then so it is actually slowing down as well, but this time it's slowing down in the negative, right? Because we're going from positive to negative. Here's the positive, here's the negative. So it's going to be negative deceleration, okay, or slowing down in the negative direction. So I'm just going to say negative deceleration. My handwriting is really not that bad. It's just writing on glass that's really hard. Let's see if I can do that better. I'm going to try and write it as best as I can. Okay. Negative D. See? That's not too bad. Right, moving on. What is happening in each of these positions? Let's have a look. So we've got position A, B, C, and D. Now remember, always look at the graph, because if it's a velocity time graph, it's different to position time graph. Velocity time tells you the velocity, position time tells you the position. Right, so if we look at A, we already decided that's going to be constant speed. Constant speed in the positive direction. So that's what's happening here. A is constant speed. B is what? What's happening in B is that nothing. It's actually not moving. So it's like a car that's moving to the traffic light. The car was moving at constant speed. It stopped at the traffic light, which is at 15, position 15 meters. Then what happened? It realized it just crossed the line maybe. It was too far forward, so it moved back. it moved back 10 meters. Okay, it moved back to position 5. And then it didn't accelerate forward. It moved forward really fast, much faster than it did at A. Okay, that's what happened. So forward, stopped, backwards, moved forward again. And looks like it moved at the same speed as A, actually. Not much faster, at the same speed. Because that's 5 meters per second. Is it? No, that's 3 meters per second. And that one is... Oh, it's a bit hard to tell. Let's work it out. So anyway, moving forward, stop, moving in negative direction, moving forward. Could you calculate the velocity in each portion? Let's do it. Let's do it so we can find out whether D is the same as A or D is steeper than A. It looks like D might be steeper than A. For A, the speed is going to be 15 because it's rise over run. 15 over 5, so that's going to be 3 meters per second. For B, it's going to be 0 meters per second. For C, how do I calculate C? What's the final position? The final position is over here. That is 5. So remember, it's rise over run. So 5 minus, what's the initial position? 15. 5 minus 15 over, that's the rise. 5 minus 15 is the rise. Now we've just calculated the rise. 5 minus 15 over 5 seconds, because the time is 5 seconds. 10 to 15 means the time is 5 seconds. But what do you notice about that? It's negative. So negative 10 over 5, which equals negative 2 meters per second. Does that make sense? It's negative? Yes, it makes sense because it's going backwards. That's actually what we expect to see. Right, what's happening in the last one? The last position is 30, the initial position is 5. So this is 25 over 5 seconds. So no, it is faster. It's 5 meters per second for that one. Okay? So that last one is 5 meters per second. So this is the fastest portion. Okay, and it's constant speed. It's not accelerating, it's just constant speed. The acceleration happens at this point over here at the corner. Because what is acceleration? Acceleration is change in velocity, which means change in direction, or change in speed, in magnitude. That's what acceleration is. We're going to talk about acceleration next week in more detail. But generally speaking, acceleration is change in velocity, which could be change in speed or direction. And this happens at the corners. So there is acceleration here, there is acceleration here, and there's acceleration here. Okay? But anyway, that's just a little idea about what we're doing next week. Check your understanding. Which runner won the race? Okay, so we've got Albert, Bob, and Charlie, and they're all running, and we're trying to find out which runner won the race. Well, they're all running the same race, so the distance is 100 meters at the end. But which one won the race? Well, the one who finished the race in the shortest time. And the one who finished the race in the shortest time is Albert. Okay, he reached it in 12 seconds. Which runner stopped for a rest? And the one who stopped for the rest was Charlie. Maybe he dropped something along the way and he stopped for about 5 seconds. Yeah, looks like it. 8 to 13. So Charlie stopped for a rest at 50 meters. So there it is, 50 meters. Yeah, 50 meters. He stopped for about 5 seconds. How long did he stop for? 5 seconds. How long did Bob take to complete the race? Where's Bob? Bob is over here. He took 14 seconds. 14 seconds right there. Okay, Bob took 14 seconds. Calculate Albert's average speed. So I'm hoping you're pausing this and doing it yourself. Albert's average speed is going to be, well, speed, as you already know, is distance over time, which equals, speed equals 100 divided by 12. 8 point something. 8.3. There you go. Meters per second. Okay, I hope that wasn't too hard. Moving on. Okay, so here we come to the fun stuff. So turns out there is this formula. Y equals mx plus b, or mx plus c, depending on what you've learned at school. And this formula is quite magical, really. The formula means y, which stands for final position, or xf, equals m, the slope, x, what is x? X is time. And then b is the y-intercept or the initial position, xi, which is the initial position. So that's what it means. So in this case, for this one here, for example, let's look at the gradient. The gradient is going to be 4 over 2 seconds, 4 over 2, so it's going to be negative 2, because it's 4 divided by 2. So it's, but it's actually 0 minus 4, which is minus 4 divided by 2, because it's going the other way. Let me explain that one more time. If I'm trying to work out the gradient of this line, I can go, well, let's take the whole line. The final position over here, the final position is negative 4. Remember, it's rise over run. The initial position is 4. The final, that's the rise. The run is 4 minus 0, which is 4 seconds. So now it's going to be minus 8 divided by 4, which is negative 2. That's the slope. So if I'm going y equals mx plus b, I just found the slope, which is negative 2. And the time, well, I'm just going to write t plus b. What is the starting point? It's 4. So that's the formula of the line. That is the formula of the line. What does this mean? It means if I give you the time, you should be able to tell me the exact position based on this formula. How so? Let's say I give you the time is 2 seconds. What is the position? Y equals minus 2 times 2, because I just told you the time is 2 seconds, plus 4. So it's going to be 0 meters. Well, let's check. At 2 seconds, it's 0 meters. Yes, that works. What if I tell you the time is 3 seconds? So it should be minus 2 meters. Does it work? At 3 seconds, it's minus 2. Yes, it works. And that's what this means. Okay, don't worry about this too much, because we're going to do it again in the future. I just wanted to give it to you just in case you're interested, for those students that are interested. Okay, and here's an example. Let me just take all of this off so I can solve number 23. Number 23 says, it's amazing how fast you can get through this when you're not in the classroom and people are making noise and asking questions. You just go. The following is an equation describing the motion of an object. Draw the position time graph for the motion from 0 to 4 seconds. Okay, that's so easy. All we have to do is put the time in. So, okay, I'm just going to put dt, which is this, and then a time, and I'm gonna go 0 to 4 seconds, 0, 1, 2, 3, 4, and then I can plot it. When time equals 0, 0 times negative 5 is 0 plus 10. So at 0 time, because remember time goes at the bottom, at 0 time, this position was 10. So we'll assume this is 10. At 1, it was negative 5 plus 10, which is 5. At 2, it was 0. At 3, it was negative 5. Oops, I think I need to get rid of this now. That's at 3 seconds. And at 4 seconds, which is over here, it was negative 5 times 4. Negative 5 times 4, which is negative 20, plus 10, negative 10. So that's what it looks like. Okay, try and line it up properly. That's what that looks like. Moving on. Practice 8. Write a quick statement about what is happening here. A car starts off at 0, moves forward to position 10, reverses back faster than it moved forward. How do I know that? The slope is steeper. Can I calculate the exact speed? Yes, I can. Rise over run, but I'm not going to do it. 15 over 1.5. just 10 meters per second for that one. So anyway, so that's positive constant speed, negative constant speed, but faster than the constant speed earlier. And then what happens here is it stops at the position of -5. That's all you need to say. 3 statements. Moves positive constant speed, negative constant speed, and then stops at -5. Interpret graphs. A small gauge train moves slowly back and forth along a straight segment of track. The position time graph for the train is shown below. During which portion of its motion, A, B, or C, does the train have the smallest speed? Looks like it's A. Oh, is it? No, hang on. It's B. Because it's the smallest slope. B. Why? What is the smallest speed? B, because the slope is the least steep. I think it's B. Let's calculate the speeds. The rise in the first one is 1, 2, 3, 4. That's 4 divided by 2, so that's 2 meters per second here. Let's do C. C is going to be huge. C is going to be 7 divided by 3. Is it 7? Yes. 7 divided by 3, which is approximately 2.2 meters per second. And then for this one here, it's going to be 1, 3, so it's 3, but -3 divided by 2, which is -1.5 meters per second. So that's what that is, -1.5. That's if you worked it out, so please work it out. It's going to be, I'll just do the workout here again. It's rise over run, so it's -2. For portion B, I'm doing it. -2 minus 1 over 4 minus 2. So it's going to be -3 over 2, which is -1.5 meters per second. Calculate the position of a ball as a function of time is given by this. Oh, just a second. So it's going to be, what is the position of the ball at 1.5 seconds? Now remember, time is over here, so it's y equals mx plus b, right? But then what they did here was y equals b plus mx. So just be careful with that, because sometimes they can move it around. Anyway, we put the 1.5 in here. So -5 times 1.5, which is -7.5. So it's going to be 3 plus -5 times 1.5. And so it's going to be 3 plus -7.5, which equals x equals -4.5 meters. Yep, that should be about right. Next, what is a speed time graph used for? I'll be right back. Okay, assalamu alaikum. Welcome to part 2. We're just taking a quick break and now we're back. What is the speed time graph used for? Used to show an object speed at a given time. Okay, so unlike the position time graph that we were talking about earlier, this time it's speed time. So we've got speed on this axis over here, and we've got time on this side over here. So speed on the y-axis, time on the x-axis, obviously. And we've got the gradient in this case does not represent velocity or speed. The gradient represents acceleration. Okay. So this here is an example of what speed time graph could look like. In this case, if it does have a gradient, then it represents acceleration, which means it is going to be speeding up. It's not going to stay the same. This does not mean constant speed. This means constant speed. Because remember, this is speed now. So let's say, for example, the speed here is 10, 20, 30, 40, 50, 60, 70. Constant speed at 40 looks like this. What happens here is the speed is getting more and more. So we started off at 0, but then after 1 second it was 10, and then after 2 seconds it was 20. So it's increasing. After 3 seconds it's 30, 40, 50. So this is going to be accelerating. Okay, and of course, one more really important point. The area under the graph represent the displacement or the distance, depending on whether we're talking velocity time. If it's velocity time, then the area under the graph represents displacement. If it's speed time, then the area under the graph represents distance. Okay, let's try and solve this problem over here. We've got a pair of cameras, a pair of cameras. Spot your number plate. Start a timer and then spot your number plate again, leaving traffic calming zone. So here we go. We've got a car, and this is the start, point A, and this is point B. The speed cameras record that your car takes 350 seconds to move between them. Calculate the average speed for your car. Of course, we should know by now that speed equals distance over time, and therefore it's going to be, speed is going to equal 800 divided by 350. And that's going to give me the answer, which is going to be 2.29 meters per second. Don't forget the meters per second. As we've mentioned earlier, the area under the graph of a speed time graph, of velocity time graph, represents the distance or displacement. Okay, so let's say, for example, here I've got the velocity and here I've got the time, and it looks like that. What is the total displacement? It's going to be the area under the graph. Okay, and I'll show you how to calculate that. So features of velocity time graph. So these are the main features. A velocity time graph shows the speed and direction an object travels over a specific period. The gradient represents acceleration. It does not represent velocity. It does not represent speed. It represents acceleration. Acceleration is change of velocity over time and measured in meters per second squared. And to calculate distance traveled, you need to find the area under the given curve or line. So the graph below describes a 50-second car journey, for example. Okay, so what do we have here? We've got part A, B, C, D, and E. We've got different points. Part A represents a positive acceleration. It's speeding up. How do I know it's speeding up? Look at the gradient. We started at 0, and then as time goes by, the speed increases. So at 5, it was over here. At 10, it's over here. So it's increasing, it's speeding up. That's what we call acceleration. What's happening at B is that it's constant speed. At B, the speed is not changing. So we call that constant speed. Okay, no gradient, constant speed. What's happening at C? It's accelerating again. The speed is changing, but not as much as A. Not as much as the spot here. Not as much as AB. So CD, there is acceleration, but this time it's not as much. CD is also acceleration, but not as high as AB. And then DE, we've got negative gradient, so that means deceleration or slowing down. How is it deceleration? Well, remember, this is a speed time graph. At point D, the speed was 25 meters per second. 25 meters per second. At point E, the speed is 0 meters per second. So it is in fact slowing down, and as you can see, it's slowing down as the car is moving. It is slowing down. Okay, so that's all that means. It means it's slowing down. So a slightly different scenario to a position time graph. A position time graph tells us position. A speed time graph tells us speed. So make sure you're looking at the axis. You're looking at the y-axis, and you're looking at what it says. If it says position time graph, it's completely different to speed time graph. Speed time graph, the gradient tells us acceleration, and the area under the graph tells us the tells us the displacement or the distance traveled, depending on whether it's velocity time or speed time. To calculate the distance traveled, we need to find the area formed under the graph. Let's do an example. The graph below describes a 50-second car journey. Find which section in the graph has the greatest acceleration. So obviously the greatest acceleration is going to be the area of the graph, or the portion of the graph with the greatest slope or the greatest gradient. So that's going to be AB. Just by looking at it, I think it's going to be AB. So how do I work it out? Once again, it's rise over run. So what I'd like you to do is I'd like you to pause the video and try and do it yourself. You can see the first one is going to be 15 minus 0 over 10 minus 0, so it's going to be 1.5 meters per second. I'm just going to write it over here to make it easier. Squared, because it's acceleration. So it's 15 meters per second or 15 meters per second squared, or 1.5 meters per second squared. Next one, there's no acceleration whatsoever, so it's just going at 15 meters per second. There's no acceleration, so it's 0 meters per second squared. The next one is going to be 25 minus 15, which is 10, divided by 10, which is 1 meter per second squared. I think I've worked it out here somewhere. And the last one is going to be negative. Why negative? Because it's going to be 0 minus 25, so negative 25, divided by 20. So it's going to be negative 25 divided by 20, so minus 1.25 meters per second squared. And the question was, where's the greatest acceleration? Obviously, the greatest acceleration was A to B. AB has the greatest acceleration. The graph below describes a 50-second car journey. Once again, work out the total distance traveled by the car. Interesting. Total distance is going to be area under the graph. So how do we calculate the area under the graph? We got to cut the graph up into different areas. So here we have a triangle. So 10 times 15, which is 150 divided by 2, so that's 75. Area of triangle is half base times height. Or if you want to, base times height divided by 2. So that's what that is. For this portion here, half base multiplied by height, which is going to be 5 multiplied by 15, or 75. What about the next area? The next area is a rectangle, so it's just base times height. So 10 times 15, which is 150. Over here, you can cut it up as well. Oh, you don't have to cut up the last portion. I can cut up this portion here into a triangle and a rectangle. Makes it easier. So once again, I'm going to work with this first. That's going to be 5 multiplied by 25. So no, is it? 5 multiplied by 10, because it's 15 to 25. So 5 multiplied by 10. And 5 multiplied by 10, that means that's 50. While the bottom is going to be 10 multiplied by 15, so 150. Please make sure that you pause the video and do this yourself before I do it. But you can still do it now. Pause it, do the last part. The last part is going to be half base times height again. So 20 multiplied by 25. Obviously that's 500, 250. And you just add them up. So it should be about 450, 675. So I've cut them up and then I've worked it out as well over here. So if you want to, you can take your time. But that's definitely the same answer that I got, 675. Do it yourself, okay? If you're not sure, do it yourself. Okay, if you thought that was difficult, go back. Just all you have to do is go back in the video. Go back to this point, okay? In the video. And just pause it. And then do it yourself. And see if you can get the same answer, okay? That's how you learn. Okay, let's look at this one here. Calculate the distance from velocity time graph. The velocity time graph is shown below for a cycle. So what is going to be the total distance? I'm going to cut this into 3 portions. 2 triangles and a square in the middle by the looks of things. Let's see if we can work it out. I would like you to do this before I do it, before I reveal the answer. So obviously those are the different areas. Why is that? Because that one's going to be half base, so it's going to be 2 multiplied by 10, so that's 20. The next one's going to be 10 multiplied by 10, which is 100. And the third one's going to be 3 multiplied by 10, which is 30. So it's going to be a total of 150, isn't it? 150 meters. Let's check our understanding. What is happening at the marked section of this velocity time graph? Remember, it's velocity time. It's not position time. If this was position time, I could say that it's not moving. But it's not position time, it's velocity time. So it's moving at constant velocity in this case. Or constant, wait, is it velocity time? It should say constant velocity. Now, assuming that is speed time, similar but not exactly the same, then it's going to be C. Okay? How do you find the acceleration from a velocity time graph? Well, we already know that it's the gradient. Okay, the gradient. Next, please make sure you pause and you do it yourself before I reveal the answer. What is happening at the marked section of this velocity time graph? What is happening? It is decelerating, it's slowing down, because the velocity here was high and the velocity here is low. So it is decelerating or slowing down. So the object is slowing down. There you go. What's happening over here? So let's summarize very quickly. What is the difference between scalar and vector quantity? Oh, now we're going back. Scalar has magnitude or size. Vector quantity has magnitude, size or size, and direction, as well as direction. What is the difference between? So things like distance is scalar, displacement is vector, speed is scalar, while velocity is a vector because it has direction. Acceleration is a vector as well. What is the difference between distance and displacement? Distance does not have a direction. Displacement has a direction. Distance is the complete journey, while displacement is the shortest distance between 2 points. So the shortest distance or a straight line between 2 points is displacement. How is ticker timer used to make dot diagrams of motion? It's a tape attached to a car or whatever, and then it makes 50 dots every second as the tape moves. If the dots are far apart, then it's moving fast. If the dots are close together, then it's moving slow. Do you know the difference between speed and velocity? I hope that you're answering these questions before I answer them. Pause the video. Do you know the difference between speed and velocity? Speed is distance over time. Velocity is displacement over time. Okay? And speed doesn't necessarily have a direction, but velocity does. What does the slope of a position time graph tell us? Remember, position time graph, the slope of a position time graph tells us the speed or the velocity. Well done. But what is the slope of a velocity? What is the slope of a velocity time graph tell us? It tells us the acceleration. The slope of a position time graph tells us speed. So this tells us speed. While if it was a speed time graph or velocity time graph, it would tell us the acceleration. What does the area under velocity time graph represent? It represents the distance traveled or displacement. If I want to be pedantic, then it represents displacement because we're talking about velocity. Show of hands, how many of you found this topic easy? I can't see you, but I hope everybody has their hand up. If you found it challenging, don't worry too much about it because we're going to revisit this throughout the year. Anyway, take care, over and out. I'll see you in the next one.